All right, here is a video explaining our day 3 notes on proving quadrilaterals with slope and distance formula. So the first proof is proving that we have an isosceles trapezoid, which it's really important to note that anytime we prove an isosceles trapezoid, you have to prove it to be a trapezoid first. So that's what this work is showing right here. I'm going through and I'm finding the slope of AB, which rise over run shows that it's 1. Same thing with DC. You can see my little staircases. Because those slopes are the same, that means that AB must be parallel to DC. So I have the math, I'm explaining the math. Now the theorem is, if at least one pair of opposite sides is parallel, the quad is a trapezoid. Therefore, ABCD is a trapezoid. Okay? Now the next part is moving on to how can I show that this is isosceles? Now there technically are 2 ways to do this. You could prove congruent legs or congruent diagonals. Now in this proof I took a really easy approach because I noticed that the legs could easily be counted. This is 4, this is 4, and that's where I'm stating that here. I explain then the math. BC is congruent to AD because distances are equal. I relate it back to a theorem. So if the legs are congruent, the trapezoid is isosceles. And now I can conclude, because I already proved it a trapezoid, this is taking care of isosceles, I can conclude ABCD is an isosceles trapezoid, which is what it wanted me to prove. Now, for just your own reference, if you were to do the distance formula or a Pythagorean theorem shortcut to find the distance of DB or AC, the radicals would end up being the square root of 40 and the diagonals are congruent, but that just probably wouldn't be my choice because the legs were just so easy to be able to compute in this situation. All right, so now we're going to move on to the next proof. I want to prove that ABCD is a rectangle. Now what I want to point out is that I gave you it's a parallelogram, which is great because then that means I don't have to prove it to be a parallelogram. So I took the approach of proving that there was a right angle. Now technically I could have done any of these, A, B, C, or D, but I just chose angle A. The sides that make up angle A are sides AB and AD. And the slope of AB is 2 over 0, which is undefined. The slope of AD is 0 over 3, which is just 0. Now, these are not negative reciprocals per se, but they are always slopes that will end up being perpendicular segments. So, this is a new way we write it up. First thing I say is 0 and undefined slopes create perpendicular lines, so AB is perpendicular to AD. Therefore, so angle A must be a right angle because perpendicular lines form right angles. So these are the 2 things, I'll put a little star here, that you would have to write. Again, I'm not really talking about negative reciprocals, but I'm emphasizing the fact that I know that 0 and undefined slopes always make perpendicular lines. So just a little bit different than what we did on our previous lesson. I tied it back to a theorem. If a parallelogram, which I have, has one right angle, it's a rectangle. Therefore, ABCD is a rectangle. All right, moving on to the next proof. So now I want you to prove a rectangle, but notice how I didn't tell you that it was a parallelogram. That means I have to prove it to be a parallelogram first. Now, you honestly have a bunch of options for that. You could do what we did in our prior lesson and prove the diagonals bisect each other by using the midpoint formula. You could show one pair of opposite sides both congruent and parallel, which means that would be the distance and the slope formula. For me, I always think it's just the easiest to go for your slopes. So I went through and I found the slope of A, B, and CD because we went down 2 over 1, down 2 over 1. And then I did the same thing for BC and AD. So up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2. So that's the math. Now remember, you're explaining the math. So I stated that they were parallel because slopes are equal. Then I tied it to a theorem. If both pairs of opposite sides are parallel, the quad is a parallelogram. And then I can conclude, partially here now, that ABCD is a parallelogram. Okay, now I got to tackle the rectangle part of this. So just like the last example, I am going to take the approach of proving that there's a right angle. You can pick any angle here, A, B, C, or D, but yet again, I decided to do angle A. Now, here's what's nice about doing the slope first to prove a parallelogram. I can now double dip into my math. Remember how I already know the slope of AB and AD? If you come up here, that's why these are like circled. Those are negative reciprocal slopes. So I said -2 and 1/2 are negative reciprocals, so AB is perpendicular to AD. Angle A is a right angle because perpendicular lines form right angles or create right angles. So, like I said, I was able to double dip in the math, explain the math, and then tie it back to a theorem. If a parallelogram has a right angle, it's a rectangle. Therefore, ABCD is a rectangle. Now, I took this approach of using the slopes to be strategic, because if I did the slopes to begin with, then I could reuse them for the second part. But just keep in mind that if you really wanted to, another way you could approach rectangle is you really could prove the diagonals congruent. Again, probably wouldn't be my first choice. I think it's so much easier just to use the slopes and prove a right angle. But hey, if you wanted to do distance formula or Pythagorean theorem to talk about these distances, I mean, I guess in this way you could really count that distance and then you'd have to get it to match on the other way. Totally an option, just not something that I personally would do, but is correct. Now, for this proof in our notes, it is prove a square, which technically means you'd have to prove it to be a parallelogram first. But just to save time and space in the notes and honestly your hand, let's just pretend I gave you that this is a parallelogram. So it's just one less thing for you to have to prove. So if I prove a square, that means I'm going to have to do both a rectangle and a rhombus. So I approached it as doing a rhombus first. Just made a decision. You could do rectangle first, doesn't really matter. Now, just to keep things simple again, I just think slope formula is so easy to use. You're seeing me draw in the diagonals, and then I stated the slopes of my diagonals. So the slope of PR is down 1/2, so that's a slope of -1/2. SQ is up 2/1, up 2/1, so that's a slope of 2/1. Those are negative reciprocals, so therefore it must be true that these segments are perpendicular. Now remember, again, you don't need a right angle. I don't need that second part of that in this situation. I just needed to prove the diagonals were perpendicular. Here's my theorem. If the diagonals of a parallelogram are perpendicular, it's a rhombus. I actually forgot my little conclude here. Therefore, PQRS is a rhombus. So I'm kind of doing like little conclusions down the way here. Okay, so now I did rhombus, so now I'm going to move on to rectangle. So again, pick any angle you want. It looks like I picked angle Q. I looked at my slopes of PQ and QR. PQ was up 1/3. QR is down 3/1. So now I'm going to say, all right, well, I know those are negative reciprocals, so therefore I have perpendicular segments. Therefore, angle Q is a right angle because perpendicular lines form right angles. I tie it back to my theorem. If a parallelogram has one right angle, it's a rectangle. Therefore, PQRS is a rectangle. Okay, so notice how I did like two little mini proofs in here. I did a proof of a rhombus and I did a proof of a rectangle. Now, remember what you have to do. You still have to tie it back to square. So, since I did these two separate little mini proofs, all I have to do is tie it back to this theorem. A quad that is both a rectangle and a rhombus is a square. Therefore, PQRS is a square, and that's what ties it back to what I was getting to begin with. Okay, Now, again, this is just the approach that I took to doing a square, which I think is the easiest, just using slope all over the place. But if you wanted to prove a rhombus by showing two consecutive sides congruent, you could do that. So I'll even put a little note here. Or two consecutive sides congruent, which means you would be using the distance formula or Pythagorean theorem. I, yet again, did rectangle by showing I had a right angle, but you could have also done congruent diagonals. Okay, so just other options that you guys could do, but in my opinion, like I said, I think this is the easiest approach. All right, so there was just one more proof here on the next and last page of our notes for today, which is proving an isosceles right triangle, which means I'm proving isosceles and I'm proving right. Now, I just went in the order given, so isosceles. That's where I'm tackling showing two congruent sides. So you guys can see my work here on the grid. The dimensions of these little right triangles I've created are 2 by 4. So here's my distance. You guys are seeing I'm getting radical 20 for each of those. There's my math. I explained my math, I tied it to a theorem, and then I concluded. Okay, and you guys have done isosceles triangle a few times at this point. Right triangle we did in yesterday's lesson as well, where I wanted to prove angle R is a right angle, which means I'm looking at these slopes, TR and RS. So it looks like TR has a slope of up 2 over 4, or 1/2. RS is down 4 over 2, which is the same thing as -2. These are negative reciprocals, so they create perpendicular segments. That means that angle R must be a right angle because perpendicular lines form right angles. I tied it back to a theorem. If a triangle has a right angle, it's a right triangle. Therefore, triangle RST is a right triangle. And then, I'm going to do one final conclusion here. Therefore, triangle RST is an isosceles right triangle. And that ties it all back in together with what I was originally asked to do in my proof line. Okay, so these are the 5 proofs that you guys should have already filled in your notes. If you did not fill these in and you're just watching the video now, you need to take responsibility and go on Google Classroom and fill these in. And then you can always rewatch this video too for the explanation. But yeah, so this is just using a lot of slope formula in here, some distance formula. The only thing I didn't cover in this video is using the midpoint formula, which we used to prove a parallelogram, which was in our day 2 notes. So be sure to refer back to that if you ever need it. That concludes this video.